I want you to try something for me.
Oh, starting with an assignment today. I like it.
Yeah, just a quick one. The next time you take a sip of water, I want you to just hold the glass in your hand for a second and consider this incredibly mind-bending fact.
It really is a wild thing to think about.
Right. The very molecules crossing your lips, like the actual water you are about to drink, have almost certainly been here before.
Definitely.
And I don't just mean sitting in a reservoir somewhere. I mean, those exact molecules could have once been inside a dinosaur?
Oh, absolutely. Or, frozen in an ancient glacier during the last ice age.
Yeah, or they could have been floating as a fluffy cloud over some completely distant continent, like centuries ago. Welcome to today's deep dive.
Glad to be here.
Our mission today is to explore Earth's oldest, most essential, and honestly, most beautiful recycling program. We're talking about the water cycle.
It is the ultimate recycling program.
It really is. We are going to take an unhurried step-by-step journey today, just following a single drop of water as it travels through this massive global loop.
And to really grasp the scale of that journey, we have to start with a foundational premise that kind of completely shifts how you view the world around you.
Right.
Earth essentially has the exact same amount of water right now that it has had for billions of years.
Which is just so hard to wrap your head around.
It is. We do not manufacture new water on this planet, and we don't destroy the old water. We just borrow it.
We borrow it, use it, and pass it on.
Exactly. That exact same finite supply is in this great, endless, continuous loop moving through the oceans, the sky, the land, and, well, all living things.
Okay, let's unpack this. If we are dealing with a finite, enclosed system where the water has been looping for literally billions of years, there has to be a colossal engine driving the whole thing.
Oh, for sure.
Because water is heavy. Anyone who has ever lugged like a 5-gallon bucket across the yard knows the physical weight of it.
It is surprisingly heavy.
Yeah, so what kind of force is lifting and pushing trillions of tons of this heavy liquid around the entire globe without ever stopping?
Well, the engine is actually located about 150 million kilometers away.
The sun.
It's the sun. And since the vast, overwhelming majority of the water on Earth sits in the oceans, that is where our drop's journey begins.
Makes sense.
The sun continuously beams electromagnetic radiation down onto the surface of the sea. And when that solar radiation hits the liquid, it transfers heat.
Okay.
And heat, at a molecular level, is really just kinetic energy. The water molecules start absorbing this energy, and they begin vibrating and bouncing around faster and faster.
So they are basically agitating each other until something physically breaks.
Precisely. Because water molecules are naturally sticky. They're held together by something called hydrogen bonds, which is what keeps them pooled as a liquid.
Right.
But as the sun pumps more and more kinetic energy into that top layer of the ocean, some of those molecules start moving so violently that they literally snap those hydrogen bonds.
Wow.
Yeah, they break free from the liquid surface and launch up into the air as a completely invisible gas.
And then this is evaporation, right?
Exactly. This phase change, moving from a liquid state into a gaseous state, is what we call evaporation. It is the world's largest, completely silent, solar-powered pump.
Just running all day, every day.
All day. The sheer scale of it is staggering when you consider the raw energy required to mechanically lift trillions of tons of water into the atmosphere every single day.
It's striking when you realize that this solar pump isn't just operating over the oceans either. The data in our sources completely reframed how I think about just a simple walk outside.
Oh, yeah.
Yeah, because this physical phase change, this evaporation is happening constantly. Everywhere there is water and warmth. It comes off lakes and rivers, obviously. But it is also pulling moisture right out of the dirt in your backyard after a rainstorm.
It really is.
It pulls the sweat off your skin to cool you down. And maybe the most fascinating part of the source material was the sheer volume of water being pumped into the sky by plants.
Yes, the biological contribution to this cycle is immense. Plants essentially act as living straws connecting the deep soil to the atmosphere.
Which is such a crazy visual.
Right. And it happens through a process called transpiration. The mechanics of it are brilliant. A tree will use its deep root system to draw up liquid water from the soil.
Okay.
It pulls that water all the way up its trunk, using capillary action, which is essentially water's sticky nature, allowing it to climb up narrow tubes inside the plant.
Oh, because of those hydrogen bonds again?
Exactly. Now, the tree uses a tiny fraction of that water for photosynthesis, but the vast majority is released from microscopic pores on the underside of its leaves directly into the air as vapor.
You look at a single potted fern in a living room, and it doesn't seem like a high-powered water pump.
No, not at all.
But when you scale that mechanism up to an entire forest, The numbers are wild. Think about the Amazon basin. You have billions of trees, some towering hundreds of feet high, constantly drawing up groundwater and breathing out invisible vapor all day long.
The sheer volume of liquid being physically moved from the deep earth into the sky across a whole jungle completely rivals the flow of massive rivers.
That is unbelievable.
It actually creates its own localized climate. The vapor rising from a dense forest can be so thick, it literally forms rivers of moisture in the sky above the canopy.
Wow.
So whether our drop broke free from the salty ocean or was breathed out by a broadleaf tree, it's now airborne. It is an energized, invisible gas drifting upward on thermal currents.
Okay, so our drop is now an invisible gas floating up into the sky. But if the sun is blasting apart these molecules into an invisible gas, there has to be an atmospheric ceiling where that thermal energy runs out, right?
Yes, absolutely.
I imagine that's where the visibility of clouds comes into play. The energy deficit forces the gas back into a liquid state.
That is the exact mechanism at work. Because the atmosphere gets fundamentally colder the higher you go.
Right, because the air gets thinner.
Exactly, the air pressure drops, causing the air to expand and cool. So as our invisible water vapor rises into these frigid upper altitudes, the molecules are robbed of that solar kinetic energy.
They lose their bounce.
They do. They slow down. They stop bouncing so violently. And when they slow down enough, those sticky hydrogen bonds we talked about earlier take over again. The molecules snap back together.
And what's this called?
This transition from a gas back into microscopic liquid droplets is known as condensation.
It's basically the global version of pouring yourself a glass of ice water on a hot July afternoon.
Oh, that's a great way to look at it.
Yeah, you take that cold glass outside, and within minutes, the outside of the glass is completely coated in heavy beads of water, and the glass isn't leaking.
Right.
The warm, invisible vapor in the summer air hits the freezing barrier of the glass. The thermal energy vanishes instantly, and the gas condenses into a liquid right onto the surface. The sky is basically doing that, but using cold, high-altitude air instead of glass.
It is the exact same physics. But up in the sky, those slowing vapor molecules need a surface to stick to, just like your glass.
Wait, what do they stick to in midair?
They require something called a condensation nucleus. These are microscopic impurities floating in the upper atmosphere.
Like pollution.
Sometimes, yeah. But it could also be a tiny speck of dust lifted from a desert, a microscopic grain of salt blown up from a breaking ocean wave, or even ash from a distant wildfire.
Oh, wow.
The slowing water molecules bump into these microscopic specks and clump around them. Billions and billions of these tiny liquid droplets form together, and that is what creates a cloud.
Which shatters one of the most common myths out there. I think most people subconsciously view clouds as thick smoke or just opaque gas.
Yeah, a lot of people think it's just steam.
But a cloud is actually a colossal hovering reservoir of liquid water.
It is entirely liquid, or, if it's high enough and cold enough, solid ice crystals.
Yeah.
And because it is liquid, it has immense mass.
Really? Like how heavy are we talking?
Well, a typical fluffy white cumulus cloud floating over your neighborhood can easily weigh over 1 million pounds.
1 million pounds? That's terrifying.
It sounds like it. But the only reason 1 million pounds of water doesn't immediately crush your house is because that weight is distributed across trillions of microscopic droplets.
Okay, that makes me feel a bit better.
Yeah, each one is so incredibly light that the rising warm air currents from the ground are strong enough to just keep them suspended.
So our drop is in a cloud bumping into other droplets. Eventually, what goes up must come down. Where does it go next? Because at a certain point, the physics changes.
It does.
The collision rate inside the cloud must hit a threshold where those thermal updrafts simply can't fight gravity anymore. That's when the sky basically drops the payload.
Exactly. The turbulence inside a cloud is fierce. These microscopic droplets are constantly slamming into each other, merging and growing larger and larger.
Right.
Eventually, a single droplet becomes so dense and heavy that the upward push of the warm air is completely overwhelmed by the downward pull of gravity. It falls.
And there's our rain.
Yes. This falling liquid or solid water is precipitation, what we experience on the ground as rain, snow, sleet, or hail.
Now, if that heavy raindrop plummets straight back down into the middle of the Pacific Ocean, it's a relatively short loop.
Very short.
It mixes into the salt water and just waits for the sun to blast it apart again. But when the atmospheric winds push those million-pound clouds over the coastline and the payload drops onto land, things get wild. The behavior of that water completely transforms the planet's surface.
It really does. It transitions from being just a weather phenomena to becoming a full-blown geological force.
How so?
When precipitation hits solid ground, the immediate consequence is often runoff. Water will always seek the lowest possible elevation because of gravity.
Right, it flows downhill.
Exactly. It pools together, trickling across the dirt, merging into streams which funnel into rivers, all stubbornly carving a path back toward the sea.
And the mechanical friction of that runoff is a master sculptor. I mean, over immense stretches of geological time, the physical weight and motion of flowing water grinds away solid rock.
It's incredibly powerful.
It doesn't just flow through valleys, it literally digs them. The Grand Canyon is essentially a monument to the relentless, grinding friction of runoff trying to reach the ocean.
That's a perfect example. Yet, for all the dramatic landscape carving happening on the surface, a massive percentage of precipitation doesn't participate in surface runoff at all.
Where does it go?
It infiltrates the ground. It seeps down through the topsoil, slowly filtering through layers of dirt and clay until it reaches porous rock, like sandstone or limestone.
Okay.
The water fills the microscopic voids and fractures within the rock itself, becoming what we call groundwater.
See, I always pictured groundwater as giant, hollow subterranean caves filled with dark underground lakes.
A lot of people do, like a Batman cave situation.
Yeah, exactly. But the sources describe it more like a massive rocky sponge. The water is trapped in the tiny pores between grains of sand and rock, sometimes hundreds of feet below our boots.
That sponge analogy is spot on. And the scale of these hidden aquifers is staggering. The volume of fresh water stored in the porous rock beneath our feet is vastly larger than all the surface rivers and freshwater lakes on the entire planet combined.
That is wild.
But the critical difference between a river and an aquifer is time. A river might rush from a mountain to the ocean in a matter of weeks.
Right.
Groundwater seeps through solid rock at an agonizingly slow pace. It might move only a few inches a year.
Which means the timing of the cycle shifts from weeks to millennia. The Great Artesian Basin in Australia is a prime example of this extreme timeline.
It really is.
It's one of the largest underground freshwater reservoirs in the world, covering over a fifth of the Australian continent. But the water being pumped out of those deep bores today didn't fall as rain last year.
No, not at all.
Some of that water fell as rain over 1 million years ago and has been slowly percolating through the rock ever since.
It highlights the extreme variation in how long a single drop of water might stay in one phase of the cycle. A drop might evaporate and rain back down in 9 days, or it might fall as snow on a polar ice cap and be locked in solid ice for 100,000 years.
Wow.
It might soak into a deep aquifer and spend 2 million years inching through limestone.
Here's where it gets really interesting, though, because I am going to stop you right there. We need to address a glaring contradiction in everything we've covered so far.
Okay.
You call it a perfectly closed, perfectly endless recycling loop. But if the loop is perfectly closed, and the Earth has the exact same amount of water it has always had, the concept of a drought shouldn't exist.
I see where you're going.
Right. If the water never leaves the atmosphere or the crust, why are major cities frequently on the verge of running completely dry? With all these massive oceans and giant underground reservoirs, why are we constantly worried about having enough fresh water to drink?
It is the ultimate scarcity paradox,
Right.
and it comes down to a matter of chemistry. Yes, the planet is completely drenched in water, but 97% of it is highly saturated with salt.
Right, the oceans.
Exactly. The oceans hold nearly all of Earth's water inventory, and from a biological perspective, seawater is toxic to us.
Because of our kidneys, right.
Yes, human kidneys cannot process the salt concentration without shutting down. And if you irrigate agricultural crops with seawater, the salt destroys the cellular structure of the plants and permanently poisons the soil.
So, out of all the water on the planet, 97% is functionally useless to our immediate survival unless we put it through incredibly expensive, energy-hungry industrial desalination plants.
Correct.
That leaves just 3% as fresh water. But even that 3% is an illusion, isn't it?
It is. Because of that tiny 3%, the vast majority is completely out of our reach. It is frozen solid in the ice caps of Antarctica and Greenland, or it is buried thousands of feet deep in aquifers that we cannot easily drill into.
So what does that leave us with?
When you strip away the salt water, the ice, and the deep groundwater, the easily accessible fresh water, the water sitting in our lakes, flowing in our rivers, and resting in shallow wells makes up less than 1% of the total water on Earth. It is in the microscopic sliver.
Which completely reframes the evaporation engine we discussed in the beginning. This was a huge aha moment for me in the source material.
Oh, yeah.
Yeah, because the sun isn't just moving water from the ocean to the land. It is actively running the world's most vital purification plant.
Yes.
Because when that kinetic energy breaks the hydrogen bonds and turns the liquid into a gas, the heavy salt molecules don't have enough thermal energy to vaporize.
Exactly right. The salt is physically left behind in the ocean. The vapor that rises up into the atmosphere is completely distilled, pure H2O.
Every rainfall over land is essentially a free, non-stop delivery of freshly distilled water from the ocean. The Earth is basically running its own massive purification plant.
It's incredible.
Without that specific chemical filter built into the evaporation process, the land masses would be barren. Managing that tiny, constantly refreshing sliver of distilled water is quite literally the foundation of human civilization.
If we connect this to the bigger picture, it really becomes a matter of life and death.
Hmm.
And no place illustrates the extreme fragility of relying on this planetary delivery service, quite like the Australian continent.
Yeah, the sources use Australia as the primary real-world example. It's the driest inhabited continent on Earth.
It is, and its climate is dominated by wild fluctuations in the water cycle. You see multi-year periods where the thermal currents and atmospheric pressures shift, and the deliveries of distilled water simply stop.
Severe droughts.
Right, the land bakes under severe drought.
Yeah.
Then the patterns snap back, and you get years' worth of heavy precipitation dumped in a matter of weeks, causing catastrophic inland floods.
The sources dive into the heavy political debates surrounding the Murray-Darling Basin over there. And just to be clear to everyone listening, our goal here isn't to take a side or endorse any specific policy from the left or right, but simply to report on how these debates really illustrate the immense pressure of managing these localized water deliveries.
Absolutely. It's not an abstract academic exercise for Australians.
Right. When you have a massive river system spanning multiple states, feeding a huge percentage of a country's agriculture, and the rainfall is that erratic, the engineering required to sustain populations is just staggering.
It really is.
The debates over dams, the reservoirs, the irrigation quotas, it is all human engineering trying to capture and share these uneven deliveries of a natural cycle to feed the country.
It forces us to recognize that while the global cycle is a closed loop, the localized distribution is anything but uniform.
Definitely.
But what is truly profound is how the localized extremes are deeply stitched together on a planetary scale. Because water spends time as an invisible, drifting gas, it doesn't respect borders or geography.
It just floats wherever the wind takes it.
Exactly. The moisture transpired by the trees in the Amazon rainforest can be caught in the jet stream and travel thousands of kilometers to fall as rain on a completely different continent.
That's wild.
The evaporation off a boiling tropical ocean at the equator is what eventually dumps heavy snow on the Rocky Mountains.
So we are all basically drinking each other's runoff, essentially.
I mean, technically, yes.
But zooming out even further, beyond just moving the physical liquid around, the sources emphasize that the water cycle is also the primary conveyor belt for global energy.
This is the critical final layer to understanding the system. When we talked about the sun pumping kinetic heat energy into the ocean to evaporate the water, that heat energy doesn't just vanish once the water becomes a gas.
Where does it go?
It is stored inside the water vapor. It is called latent heat. The vapor carries that invisible solar energy up into the atmosphere and across the globe.
So the vapor is basically acting like a thermal battery.
A massive floating thermal battery. And here's where it gets violent. When that warm vapor hits cold air and condenses back into liquid droplets to form a cloud, all of that stored kinetic heat energy is suddenly released back into the surrounding atmosphere.
Which heats up the air around the cloud, right? Causing that air to rapidly expand and rise even faster.
You've got it, which then draws in more moist air from below, which condenses, releasing even more heat, creating a self-sustaining atmospheric engine.
Oh, wow.
That massive release of latent heat energy is precisely what powers a hurricane. It is what drives high-speed winds. It shapes the jet stream.
That makes so much sense.
When we talk about climate, we are largely talking about the behavior of water moving through this cycle. When you watch a catastrophic storm system on the news, you aren't just looking at falling water. You are looking at ancient solar heat, harvested from the ocean days or weeks prior, rapidly discharging into the atmosphere.
It fundamentally changes how you look at the sky.
It really does.
We started with the premise of a single drop in an epic, endless loop. From the massive solar-powered pump breaking chemical bonds on the surface of a salty ocean to the invisible thermal batteries drifting upward into the cooling air.
Hmm.
The condensation around a tiny speck of desert dust to form a million-pound cloud. The violent collisions leading to a heavy raindrop falling back to Earth, carving a microscopic groove into a canyon wall, or soaking into the dirt to slowly flow back to the sea and do it all again.
The cycle has operated flawlessly for billions of years, but there is one final lingering thought you should ponder next time you look out the window at the rain. It's the modern disruption of that cycle's timing. We talked earlier about aquifers like the Great Artesian Basin, where the water has been trapped for millennia. Today, human industrial agriculture is drilling massive bores into these deep fossil aquifers all over the globe, pumping out billions of gallons of water to grow crops in deserts.
We're mining it.
Exactly.
Yeah.
We are mining ancient water exponentially faster than the slow trickle of the natural cycle can ever replace it. It forces you to ask a very uncomfortable question.
Which is?
When we engineer our societies to rely entirely on emptying underground reservoirs that took hundreds of thousands of years to fill, what happens to the populations living above them when they finally run dry in our lifetime?
Wow. That is a sobering reality to pair with your next glass of water. It is a perfectly closed loop, but we are pulling heavily from accounts that we can't afford to overdraw.
Well said.
Thank you so much for joining us on this deep dive. Stay curious, respect the rain, and we'll catch you next time.